A spiral galaxy hangs in the void, a whirlpool of 100 billion stars. How did this cosmic masterpiece come to be? The story of galaxy formation is the universe's grandest epic, a tale that stretches from the first instant of time to the distant future. In this video, we will unravel that epic through 50 mind-blowing facts. By the end, you will understand the forces that sculpt these island universes and our own place within the stellar whirl. We will explore how invisible scaffolds shape everything and why the night sky will look utterly different in 5 billion years. What part of this cosmic story feels most mysterious to you? That initial smoothness is our first and perhaps most profound clue. Right after the Big Bang, the universe was not a scattered collection of galaxies. It was a searingly hot, nearly perfect fog, a plasma so dense that light could not travel freely. Matter and energy were spread out with incredible, almost boring uniformity. If you could take a snapshot of the cosmos at that infant moment, it would look like a featureless, glowing haze from one end to the other. Yet today, we look up and see a cosmos rich with structure, with vast empty voids and dense clusters where galaxies gather by the thousands. So how did we get from that smooth beginning to this clumpy, textured reality we call home? The answer lies in the faintest of whispers written into that early fog. Those faint whispers were quantum in nature, born from the bizarre rules that govern reality at the very smallest scales. In the searing plasma of the newborn universe, empty space itself was not truly empty. It was a seething, frothing sea of potential, where pairs of particles and their antiparticles would blink into existence for unimaginably brief moments before annihilating each other back into energy. This quantum jitter created microscopic patches where the density of matter and energy was ever so slightly higher or lower than the average. Think of it like the surface of a perfectly calm pond suddenly experiencing a trillion tiny, random ripples all at once. On their own, these quantum ripples were vanishingly small, utterly insignificant on any human scale. But then something extraordinary happened to them. The universe underwent a sudden, violent growth spurt known as inflation, expanding faster than the speed of light itself for a sliver of a second. This expansion did not create new ripples, it took the existing ones and stretched them. It took those subatomic quantum wrinkles and magnified them to sizes larger than our entire observable universe today. What was once a microscopic quantum hiccup became a continent-sized variation in the density of the cosmic fog. These stretched imperfections, frozen into the fabric of spacetime, became the universe's first and most important structures. They were the gravitational seeds. In places where the density was just a fraction of a percent higher, gravity had a tiny head start. Over the next hundreds of millions of years, that slight excess would pull in a little more matter from its surroundings, which would pull in even more, beginning a slow, cosmic snowball effect. Every galaxy cluster, every spiral arm, every star you see in the night sky owes its ultimate origin to those random quantum tremors, magnified to a cosmic scale. Our entire cosmic neighborhood, in a very real sense, was once smaller than an atom. These stretched quantum seeds needed a framework to grow on, a hidden architecture to give the universe its shape. Enter the universe's greatest unsolved mystery, dark matter. We cannot see it, touch it, or detect it with any telescope, yet it makes up roughly 85% of all the matter in existence. Its presence is felt only through its immense gravitational pull, and in the early universe, this invisible substance held the ultimate advantage. Because dark matter does not interact with light or with itself in any way except through gravity, it faced no resistance. Ordinary matter, the stuff that makes up stars, planets, and us, was trapped in that searing plasma fog, constantly buffeted by radiation pressure, unable to clump together. But dark matter was free. It could immediately begin to pool and gather within those stretched quantum wrinkles, building vast, invisible structures in the darkness. Long before the first star flickered on, dark matter was weaving a cosmic web, creating immense gravitational wells in the void. These wells are the true scaffolding of the universe. When ordinary matter finally cooled enough and escaped the plasma fog, it had a clear destination. It simply flowed like water finding the lowest point into the waiting gravitational basins carved out by dark matter. Every galaxy we see today sits at the heart of a much larger, invisible halo of this mysterious substance. Our own Milky Way is embedded in a colossal sphere of dark matter that extends far beyond its visible stars. So, while we celebrate the brilliance of stars, we must remember they are merely the luminous decoration on an invisible frame, tracing out a shape we cannot directly see. What does it mean that the universe we perceive is just the glitter on the surface of a profound and unseen depth? Gravity's patient work within that invisible scaffolding finally bore its first visible fruit. A few 100 million years after the cosmic dawn, the universe's initial smoothness had given way to a new, clumpy landscape. The first true galaxies began to flicker on, but they looked nothing like the majestic spirals we see today. These were the protogalaxies, the cosmic pioneers. They were tiny by modern standards, perhaps only 1% the mass of our Milky Way, and utterly chaotic in form. Picture a ragged, misshapen cloud of pristine hydrogen and helium gas tumbling through the darkness. There were no elegant spiral arms, no bright central bulges, no orderly disks of stars. These were raw, unformed blobs, their structure dictated entirely by the lumpy distribution of dark matter that had pulled them together, and within these gassy crucibles a furious drama was unfolding. Freed from the blinding plasma fog, the gas could finally cool, condense, and collapse under its own weight. The result was not a gentle trickle of starlight, but a violent, all-consuming firestorm. These protogalaxies did not form stars one by one. They forged them in colossal, explosive bursts. Thousands, perhaps millions of stars would ignite in a single cosmic frenzy, blazing with a ferocious blue-white intensity. These first stars were unlike any that exist today. They were behemoths, monsters dozens or even hundreds of times more massive than our Sun, composed only of the primordial hydrogen and helium from the Big Bang. They lived fast and died young, burning through their nuclear fuel in just a few million years before ending their lives in cataclysmic supernova. These titanic explosions were the universe's first great recycling events, blasting newly forged heavy elements like carbon, oxygen, and iron back into the surrounding gas, seeding it for the next generation. So the early cosmos was a place of stark contrasts, a dark tapestry sporadically lit by the brief, brilliant flares of these chaotic stellar nurseries, each one a small, messy workshop where the foundations for everything to come were being hammered out in fire and violence. Those chaotic protogalaxies were not destined to remain isolated. Their story was one of relentless collision and consolidation. The dominant force shaping the galaxies we see today is not gentle growth, but a violent, hierarchical assembly. Think of the early universe as a cosmic construction site, with countless small, irregular building blocks swirling in the dark matter scaffolding. Gravity, acting over billions of years, pulled these blocks together in a relentless game of merger and acquisition. Smaller galaxies would be drawn into the gravitational embrace of larger ones, their stars and gas mingling to forge a new, more massive structure. Our own Milky Way is a testament to this process. It was not born in its current grand spiral form. It likely began as a swarm of hundreds, perhaps thousands, of those tiny, gassy protogalaxies. Over eons, they crashed together, their combined mass creating the gravitational well that could attract even more material. Each major merger would violently shake up the galaxy's structure, scattering stars into a halo, triggering frenzied bursts of new star formation, and sometimes even destroying any orderly disk that had begun to form. We see the evidence of this ancient violence all around us. The faint, ancient stars that form a spherical halo around our galaxy's main disk are the survivors from those early, devoured building blocks, stellar fossils from a time of cosmic cannibalism. And this process is far from over. Right now, the Milky Way is in the act of digesting several smaller dwarf galaxies, and it is on an inevitable collision course with the neighboring Andromeda galaxy. In about 5 billion years, that colossal merger will completely reshape our night sky, erasing the familiar constellations and forging a new, larger elliptical galaxy. So, every majestic galaxy is not a static island, but a dynamic and ever-changing product of a violent history, a celestial metropolis built from the ruins of countless smaller towns. Mergers may have built the galactic framework, but they also gave rise to its most elegant and enduring form. Among the countless galaxies in the sky, the majestic spiral stands as a masterpiece of cosmic architecture, a perfect balance of chaos and order. Our own Milky Way is a prime example, a structure composed of 3 distinct and ancient components, each telling a different part of its history. At its heart lies the central bulge, a dense, football-shaped swarm of stars. This region is a stellar retirement community, dominated by older, redder stars that formed in the galaxy's violent, early youth. It is a crowded, golden-hued core, and for many years, astronomers believed a supermassive black hole lurked silently at its very center, a discovery we will return to later. Spreading out from this bulge is the galaxy's most famous feature, the vast, thin disk. This is where the galaxy comes alive with new creation. Imagine a spinning vinyl record, but one that is hundreds of thousands of light years across and shimmering with starlight. The disk is remarkably flat and contains most of the galaxy's gas and dust, the raw materials for building stars. Within this disk are the magnificent spiral arms, those bright, trailing curves that give these galaxies their name. These arms are not permanent structures made of the same stars, but rather cosmic traffic jams, density waves that move through the disk like a ripple on a pond. As gas and dust pile up in these waves, they compress, triggering the birth of brilliant, short-lived blue stars and glowing nebulae that trace out the arm's path. The stars themselves move in and out of these arms over time. Finally, enveloping the entire luminous disk and bulge is the galactic halo, a vast spherical cloud of ancient stars and mysterious dark matter. This halo is incredibly diffuse, but it holds some of the galaxy's oldest treasures, including dense clusters of stars known as globular clusters. These clusters are like fossilized stellar cities, each containing up to 1 million stars that formed together from the same primordial gas cloud over 12 billion years ago. They orbit the galaxy's center on long, looping paths, silent witnesses to the galaxy's earliest days. So when you look at a spiral galaxy, you are seeing a living timeline from the ancient halo and the old bulge to the young, star-forming disk, all held in a graceful, spinning balance. But what force maintains this beautiful, fragile order against the pull of chaos? That beautiful, spinning order of a spiral galaxy is not the universe's final word. For every graceful whirlpool, there exists another galactic form, one that speaks of a far more violent and final history. These are the elliptical galaxies, the cosmic retirement homes. Picture a vast, smooth cloud of stars, shaped like a dimpled football or an enormous, fuzzy egg. There are no spiral arms, no swirling disks of dust, no bright knots of newborn stars. Instead, the light is a uniform, golden red glow, emanating from a dense swarm of ancient suns. This serene appearance is deceptive, for it tells a story of colossal violence that has long since settled into a quiet, fading ember. The key difference between a spiral and an elliptical lies in its gas, the raw fuel for star birth. Elliptical galaxies possess almost none. Their interstellar space is a near-perfect vacuum, swept clean of the gas and dust clouds that could collapse to form new stellar generations. Without this fuel, the galaxy's star-forming factories have shut down permanently. The stars you see within an elliptical are almost exclusively old, red, and cool, having burned for billions of years. They drift on random, chaotic orbits around the galactic center, like a swarm of bees with no sense of direction, creating that smooth, featureless glow. So how does a galaxy run out of gas so completely? The prevailing theory points to a catastrophic origin story, one of galactic cannibalism on the grandest scale. Elliptical galaxies are thought to be the final products of major mergers, the ultimate outcome when two large spiral galaxies of roughly equal size collide. When such a titanic event occurs, it is not a simple, gentle blending. It is a gravitational maelstrom. The orderly, rotating disks of both galaxies are utterly torn apart, their stars flung onto those random, swarm-like orbits. But the real drama involves the gas. The colossal collision sends powerful shockwaves through the vast reservoirs of hydrogen in both galaxies, compressing it violently from all sides. This triggers a ferocious, all-consuming burst of star formation, a final stellar firestorm of epic proportions. In a relatively short cosmic time, the galaxy burns through its entire galactic fuel supply in one glorious, unsustainable blaze. What gas isn't turned into stars is either heated to such extreme temperatures that it cannot cool and condense, or it is flung entirely out of the galaxy by the merger's violence. The result is a galaxy left gas poor and quiescent, its star-forming days over forever. The merger forges a new, larger, and smoother structure from the wreckage of the two spirals, a celestial phoenix that rises not into new life but into a long, quiet retirement. The largest galaxies we see in the universe, the monstrous giants at the hearts of galaxy clusters, are almost always these elliptical behemoths, having grown fat through countless mergers, their spiral structures long since erased by ancient violence. Their serene, golden light is the calm after the most extreme storm the universe can muster. But the cosmic story does not end with spirals and ellipticals. Between these grand, orderly forms exist the galactic rebels, the irregulars. These are galaxies that refuse to conform, lacking any defined spiral structure or smooth elliptical shape. They are cosmic splatters of starlight, chaotic and often beautiful in their asymmetry. Some look like misshapen blobs, others resemble taffy pulled apart into strange, twisted streams. Their very existence is a testament to the dynamic, often violent, environment of the universe. Many irregulars are exactly that, the mangled wreckage of a gravitational encounter. When a smaller galaxy ventures too close to a larger neighbor, the immense tidal forces can stretch and tear it apart, pulling its stars and gas into long, looping tails without completely destroying it. The result is a galaxy permanently scarred by the interaction, its form forever altered into something unique and disordered. Other irregulars, particularly the smaller dwarf irregulars, are simply cosmic late bloomers. They are small, gas-rich systems that have lived a relatively quiet life, perhaps orbiting on the fringes of a larger group. Without the strong gravitational influences that force a galaxy to settle into a disk or be consumed in a merger, they have never had the chance to organize. They remain in a state of perpetual, youthful chaos, their abundant gas fueling constant, vigorous bursts of new star formation. This makes them some of the most fertile stellar nurseries we can observe, glowing with the intense blue light of massive young stars and the pink glow of vast hydrogen clouds. So while they may lack the majestic architecture of their larger cousins, irregular galaxies are vibrant, energetic, and crucial pieces of the cosmic puzzle, reminding us that not all structure in the universe is neat and tidy. Some of the most creative and prolific places are wonderfully, beautifully messy. This messy, creative chaos of irregular galaxies is not always a permanent state. Often, it is merely a prelude to a final, one-sided feast. The hierarchical assembly of the cosmos has a darker, more predatory side, a process astronomers call galactic cannibalism. It is exactly what it sounds like, The largest galaxies in the universe do not grow solely from peaceful mergers of equals. They achieve their immense size by systematically devouring the smaller satellite galaxies that orbit them, absorbing their stars, gas, and dark matter into their own vast structure. This is not a rare or ancient event. It is happening right now in our own cosmic backyard. Our Milky Way is a practicing cannibal, and its current meal is the Sagittarius dwarf spheroidal galaxy. This tiny companion, containing perhaps only a few 100 million stars, has been orbiting the Milky Way for billions of years. With each pass, our galaxy's immense gravitational tide pulls at it, stretching it like cosmic taffy. The process is slow but relentless. Streams of stars are being ripped from the dwarf galaxy, not in a single violent event, but in a continuous, graceful unraveling. These stolen stars are now being strewn across the Milky Way's halo, forming great, faint ribbons that wrap around our entire galaxy. Astronomers can actually map these stellar streams. They appear as subtle overdensities, faint rivers of stars flowing through the darkness, all moving together on similar orbits. By tracing these streams, we can reconstruct the dwarf galaxy's original path and even estimate how many times it has circled the Milky Way, each orbit costing it more of its substance. Eventually, the Sagittarius dwarf will be completely dissolved. Its identity will be erased, its stars assimilated into the halo of the Milky Way, becoming indistinguishable from the other ancient stellar fossils there. This is the ultimate fate of most small galaxies that venture too close to a giant. They become part of its history. There remains a ghostly signature in the light of their consumer. Our galaxy's halo is thus a galactic graveyard, filled with the digested remains of countless such meals, a silent record of billions of years of cosmic predation. The ghostly remains of consumed galaxies sink into the halo, but the true gravitational heart of a large galaxy lies far deeper within its core. Lurking in the center of nearly every massive spiral and elliptical galaxy, including our own Milky Way, is a cosmic monster of unimaginable scale, a supermassive black hole. These are not the stellar mass black holes formed from collapsing stars. These are behemoths with masses ranging from millions to billions of times that of our Sun, all compressed into a region of space smaller than our solar system. The one at the center of our galaxy, known as Sagittarius, a star, is a 4 million solar mass giant. Its presence is felt not by what it emits, but by the frantic dance it forces on the stars around it. Astronomers have tracked stars whipping around an invisible point at speeds exceeding 5,000 kilometers per second, their orbits revealing the terrifying gravitational grip of an object with no surface, only an event horizon from which not even light can escape. The existence of these monsters poses one of the great timing mysteries in cosmology. We have detected supermassive black holes in galaxies so distant that their light has traveled for over 13 billion years to reach us, meaning they existed when the universe was less than 1 billion years old. How did such colossal objects form so astonishingly fast? Did they grow from the collapse of enormous primordial gas clouds, or were they seeded by the first generation of impossibly massive stars? Their relationship with their host galaxy is equally complex and intimate. They are not passive occupants. When a black hole actively feeds, pulling in vast amounts of gas and dust, the infalling material heats up to millions of degrees and blazes with radiation, creating an active galactic nucleus, the most powerful sustained energy source in the universe. This furious activity can drive galactic-scale winds, heating up or even blowing away the galaxy's star-forming gas, effectively putting a brake on the creation of new stars. In this way, the supermassive black hole, a tiny point in the galactic center, can dictate the life and death of an entire galaxy spanning hundreds of thousands of light years. It is a feedback loop of staggering power where the galaxy feeds the black hole, and the black hole, in turn, shapes the destiny of the galaxy. When a supermassive black hole feasts, it does not dine quietly. It announces its meal across the universe with a brilliance that defies comprehension. This is the realm of the active galactic nucleus, where a galaxy's central monster transforms into the most powerful engine in existence. The most extreme examples are quasars, the distant beacons that outshine entire galaxies of 100 billion stars. Their secret is not the black hole itself, but the frenzied banquet happening just outside its point of no return. As vast rivers of gas, dust, and even entire stars spiral inward, they do not fall straight in. Conservation of angular momentum forces this doomed material to form a swirling, flattened maelstrom called an accretion disk. Here, particles rub against each other at fantastic speeds, creating friction that heats the disk to temperatures of millions of degrees. This superheated plasma glows with a fierce, blinding light across the entire electromagnetic spectrum, from X-rays to radio waves. The sheer gravitational energy released as matter tumbles toward the event horizon can be tens of times greater than the energy from nuclear fusion in all the galaxy's stars combined. But the spectacle does not end there. Along the black hole's spin axis perpendicular to the disk, some of the infalling material can be channeled and accelerated by immensely powerful magnetic fields. This creates two narrow, opposing jets that blast outward at nearly the speed of light, punching through the galaxy and extending for thousands, even millions, of light years into intergalactic space. These jets are made of a soup of relativistic particles that shine brilliantly in radio waves, often appearing larger than the host galaxy itself. To witness a quasar is to see a pinprick of light that outshines a cosmic metropolis, a testament to the raw, transformative power locked within gravitational singularities. It is a temporary phase in a galaxy's life, a brilliant fever dream of consumption that eventually fades as the fuel runs out, leaving behind a quiet supermassive black hole and a profoundly changed galaxy. That brilliant fever dream of a feeding black hole leaves a permanent mark on its galaxy. The torrents of radiation and the relativistic jets from an active nucleus are not just a light show. They are a force of galactic engineering capable of sculpting a galaxy's future on the grandest scale. This leads us to a crucial and violent process in galactic life, the phenomenon of galactic winds. These are not gentle breezes, but million-degree tempests of gas streaming out of a galaxy at speeds that can exceed 1,000 kilometers per second. They are driven by two of the most energetic events a galaxy can host, the collective fury of newborn stars and the focused fury of a central black hole. In regions of intense star formation known as starbursts, massive stars live fast and die young. Their powerful stellar winds and ultimately their supernova explosions act like countless cannons firing in unison. The combined energy from these events can overwhelm the galaxy's gravity, blowing a vast bubble of hot gas that punches right out of the galactic disk, carrying with it a significant portion of the galaxy's interstellar gas reservoir. Similarly, an active galactic nucleus acts as a single, unimaginably powerful engine, its radiation pressure and jets directly heating and pushing gas outwards. The consequence of these winds is profound and permanent. This ejected gas is the very raw material, the hydrogen fuel, required to form the next generation of stars. By violently expelling it into intergalactic space, the galaxy is essentially robbing its own future. It is a self-regulating, or more accurately, a self-limiting mechanism. The very processes that create brilliant starlight also work to snuff it out by removing the fuel. Astronomers call this quenching. A galaxy that experiences a powerful, sustained wind can see its star formation rate plummet, its stellar population age, and its spiral structure fade. In essence, the galaxy's most vigorous period of life plants the seeds of its own retirement. We see evidence of this in many massive elliptical galaxies which are gas-poor and quiet. Their frenzied youth, marked by either colossal starbursts or furious black hole activity, likely drove winds so powerful they cleared the galactic stage, leaving behind a serene but fading glow of ancient stars. The galaxy, in a fit of creative fury, consumed its own potential. Those galactic winds and violent mergers create an astonishing diversity of shapes in the night sky. To make sense of this cosmic zoo, we needed a way to organize our observations, a family album for galaxies. This brings us to one of the most famous tools in astronomy, the Hubble sequence. In the 1920s, the astronomer Edwin Hubble, using the powerful new 100-inch telescope at Mount Wilson, began to meticulously catalogue the shapes of distant galaxies. He noticed patterns and grouped them into a simple, elegant classification system. At its heart are the two main branches we have already met, the spirals and the ellipticals. Ellipticals are arranged by how round or flattened they appear, labeled from E0 for perfectly spherical to E7 for the most cigar-shaped. The spirals are split into two branches, ordinary spirals, labeled S, and barred spirals, labeled SB, which have a prominent central bar of stars cutting through their nucleus. Each branch is then further ordered by how tightly wound the spiral arms are and the size of the central bulge. Hubble arranged these types on a diagram that looks remarkably like a sideways tuning fork, with the smooth ellipticals at the handle, splitting into the two parallel prongs of spiral galaxies. This tuning fork diagram became an iconic map of the galactic landscape. For decades, many astronomers interpreted it as an evolutionary sequence. They thought perhaps all galaxies began as featureless ellipticals and then, through some process, flattened into disks and grew spiral arms, or that they started as spirals and then merged into ellipticals. It was a beautiful, simple story, but as our understanding of galactic cannibalism, star formation quenching, and dark matter grew, a more complex truth emerged. The Hubble sequence is not a timeline. It is more like a family portrait showing different life paths. An elliptical galaxy is not an aged spiral. It is the product of a specific, violent history of major mergers that destroyed its disk. A grand design spiral with loose arms is not necessarily older or younger than one with tight arms. Its shape is dictated by the density of its disk and the dynamics of its density waves. The tuning fork, then, is a snapshot of galactic diversity frozen in time, a testament to the different recipes of mergers, gas content, and internal dynamics that forge a galaxy's identity. Hubble gave us the vocabulary to describe the shapes, but it took a century of discovery to understand the dramatic stories behind each portrait. Hubble's tuning fork captures individual galaxies, but it misses the larger truth of their social nature. Galaxies are not isolated islands drifting in an empty sea. They are profoundly social creatures, gathering in groups, flocks, and immense cities that represent the very largest structures gravity can build. Zoom out far enough from any single galaxy, and you will find it is part of a family. Our Milky Way, for instance, belongs to a modest gathering called the Local Group, which includes about 60 galaxies, with Andromeda and our own as the dominant giants. But this is just a small neighborhood. The true titans of the cosmos are galaxy clusters. These are the metropolises of the universe, colossal gravitational wells where hundreds, sometimes thousands, of galaxies are bound together in a single, teeming system. The nearest great cluster to us is the Virgo cluster, a swarm of over 1,000 galaxies about 54 million light-years away. But even that pales in comparison to monsters like the Coma cluster, which contains over 1,000 bright galaxies and perhaps tens of thousands of smaller ones, all orbiting a common center of gravity. The sheer scale is difficult to grasp. A single cluster can span tens of millions of light-years. Yet, the galaxies themselves are only the visible tip of an immense and hidden iceberg. The space between the galaxies in a cluster is not empty. It is filled with a seething, tenuous atmosphere of superheated gas known as the intracluster medium. This gas is so hot, reaching temperatures of tens of millions of degrees, that it glows not in visible light but in powerful X-rays. This intergalactic fog contains more ordinary matter than all the stars in all the cluster's galaxies combined. But even this vast ocean of hot gas is not the primary source of the cluster's gravity. The true anchor, the cosmic glue that holds this entire colossal structure together, is dark matter. Galaxy clusters are the richest reservoirs of this mysterious substance in the universe. Their immense gravitational pull, which we can measure by watching how quickly galaxies orbit within them, tells us that over 80% of a cluster's mass is invisible dark matter. The galaxies we see are merely tracing out the contours of a much vaster, unseen dark matter halo that forms the cluster's true skeleton. In this sense, a galaxy cluster is the ultimate expression of the cosmic web's architecture, a dense knot where the dark matter filaments predicted by theory intersect and pool. They are not just collections of galaxies, they are the universe's final word in structure, the last rung on the ladder of cosmic organization before the smooth, homogeneous expanse of the cosmos itself takes over. Within their vast domains, the fates of individual galaxies are written by the relentless forces of their crowded environment. That cosmic web woven by dark matter and gravity is not a permanent fixture. A more mysterious force is working on the largest scales of all, a force that is actively unraveling the universe's grand design. We call it dark energy, and its sole effect seems to be a relentless push, causing the expansion of the universe to accelerate. For billions of years, gravity was the universe's dominant architect, patiently pulling matter into filaments, clusters, and galaxies. Dark energy changes that story. Think of the cosmos as a vast, stretching sheet of rubber. Gravity acts like weights placed on the sheet, creating dips and valleys where matter collects. Dark energy, however, is like someone steadily pulling the edges of the sheet outward, making the rubber itself expand faster and faster. On local scales, within galaxy clusters or our own local group, gravity still wins. The pull between the Milky Way and Andromeda is strong enough to overcome the cosmic expansion, dooming them to a future collision. But on the grandest scales, across the voids between superclusters, dark energy's push is becoming supreme. It is increasing the distances between these vast structures, stretching the filaments of the cosmic web thinner and longer. Over time, as the acceleration continues, galaxy clusters will become increasingly isolated islands in a rapidly widening sea of emptiness. The universe's large-scale structure, once a complex tapestry, will be pulled apart into a sparse and lonely collection of disconnected galactic islands. This discovery that the expansion is not slowing down but speeding up was one of the most shocking in modern cosmology. It means the fate of the cosmos is not a gradual slowdown or a dramatic collapse, but an endless, accelerating drift into cold, dark isolation. The very force that is shaping the universe's ultimate future is also, right now, determining how far apart the grandest structures will grow. The future of the cosmos may be one of accelerating isolation, but the past is written in the stars themselves. To uncover that history, astronomers have become galactic archaeologists, sifting through the stellar population of our own Milky Way to reconstruct its ancient, violent biography. They do this not by digging in the ground, but by reading the light of countless suns. Every star is a fossil, a time capsule holding precise information about when it was born and the conditions of its birthplace. The key clues are a star's motion, its age, and its chemical composition or metallicity. A star's path through the galaxy can reveal its origin. Stars born together in the same gas cloud will move in similar ways, a shared motion that can persist for billions of years. By mapping the velocities and positions of millions of stars, we can identify these moving groups, streams of stars that are the shredded remains of ancient dwarf galaxies consumed long ago. The chemical fingerprint is even more telling. The first stars in the universe were pure, composed only of hydrogen and helium. When they died in supernova, they forged heavier elements like carbon, oxygen, and iron, and scattered them into the surrounding gas. The next generation of stars formed from this enriched gas, inheriting a trace amount of these metals. Each subsequent stellar generation builds on the chemical legacy of the last. Therefore, a star's metallicity is a direct clock. A star with very low metal content must be ancient, a true relic from the galaxy's earliest days. A star rich in metals is a more recent arrival. By surveying the galaxy, archaeologists have found distinct stellar populations with wildly different chemistries and orbits, and this is where the story turns violent. The Milky Way's smooth disk is surrounded by a halo of ancient, metal-poor stars on chaotic, plunging orbits. For decades, this was thought to be the quiet, primordial foundation of our galaxy. But detailed chemical mapping revealed something astonishing. The halo is not a single, uniform population. It is a messy amalgam of distinct streams and clusters, each with its own unique chemical signature. These are the archaeological dig sites, the evidence of separate accretion events. The most dramatic discovery came with the identification of a colossal structure now known as Gaia Enceladus, or the Sausage Galaxy. Billions of years ago, a massive dwarf galaxy, perhaps 1/4 the size of the young Milky Way, collided with our own in a head-on catastrophic merger. The violent encounter shredded the intruder, scattering its stars into the halo on very radial, sausage-like orbits, while also likely puffing up and thickening the Milky Way's nascent disk. The stars from that merger carry a specific chemical tag, allowing us to pick them out from the crowd. This was not an isolated event. Our galaxy's history is a chronicle of such meals. The ongoing digestion of the Sagittarius dwarf, the ancient remains of the Sequoia galaxy, and the Helmy stream all tell of a past dominated by relentless cannibalism. We are not living in a pristine, isolated spiral. We are citizens of a cosmic metropolis built from the ruins of countless smaller galactic settlements, their stellar citizens now forever part of our own. The night sky is not just a beautiful spectacle, it is a sprawling archaeological site, and every faint star has a story of ancient cataclysm to tell. This archaeological record of galactic cannibalism has profound implications for our own existence. The story of where we live in the Milky Way is not just about location, it is about timing and safety. Astronomers have proposed a fascinating idea, the concept of a galactic habitable zone. Just as a planet needs to orbit within a star's habitable zone to have liquid water, a star system might need to reside in a specific region of a galaxy to foster complex, long-lived life. It is a cosmic real estate theory, suggesting that not all galactic neighborhoods are created equal. The galactic center is a dangerous metropolis. Here, stars are packed together 1,000,000 times more densely than in our solar neighborhood. The radiation from countless stars and the central supermassive black hole would be intense. More critically, the sheer density of stars makes catastrophic events far more likely. A nearby supernova, the explosive death of a massive star, could sterilize entire planetary systems with lethal blasts of radiation. In such a crowded district, these events would be relatively common. Move too far out into the sparse, ancient halo, and you face a different problem, a poverty of resources. The halo is dominated by stars that formed very early in the universe's history, stars that are metal-poor. They contain very low abundances of heavy elements like iron, silicon, and oxygen, the very building blocks of rocky planets like Earth. A star born in the halo likely formed from gas that had not been enriched by many generations of supernova. It might not possess the necessary materials to form terrestrial planets at all, or only in very meager amounts. This points to a potential sweet spot, a galactic suburb. The region is the outer disk of a spiral galaxy, well away from the crowded, violent core, but still within the star-forming disk where successive generations of supernova have seeded the interstellar medium with a rich supply of heavy elements. Our own solar system resides in just such a locale, about halfway out along one of the Milky Way's spiral arms. We are far enough from the center to avoid the worst radiation and stellar density, yet we orbit a star, the Sun, that is metal-rich enough to have formed the rocky planets. Furthermore, our position may even be synchronized with the galaxy's structure. Some theories suggest that as our star orbits the galactic center, its path may keep it safely between spiral arms, avoiding the dense, shock-wave-ridden regions where star formation is rampant and supernova are more frequent. This idea of a galactic habitable zone is still theoretical, but it frames our existence within a much larger cosmic context. We are not just on a planet in a solar system, we are in a specific, perhaps privileged district of a vast galactic city. Our story written by the galaxy's own violent history of star birth, death, and chemical enrichment. That ancient, violent past we read in our galaxy's stars was not unique. It was the universal condition of a younger, more frenetic cosmos. If we could rewind the clock by 10 billion years to a period astronomers poetically call cosmic noon, we would witness a universe in the throes of its most productive and tumultuous adolescence. This is not speculation, it is a direct observation made possible by the most powerful telescopes ever built. When the Hubble Space Telescope stared at a seemingly empty patch of sky for days, collecting the faintest glimmers of light, it created the Hubble Deep Field. That iconic image revealed thousands of galaxies, not as they are today, but as they were billions of years in the past, their light only now reaching us after an epic journey across the universe. These deep field surveys are time machines, and they paint a consistent, staggering picture. The universe at cosmic noon was a dramatically more energetic and chaotic place. Star formation was not a gentle process, it was a wildfire. Galaxies were converting their vast reservoirs of gas into new stars at rates 10, even 100 times faster than the Milky Way does today. Imagine entire galaxies shining with the intense blue light of countless massive young stars, their interstellar clouds glowing with the fierce pink of energized hydrogen. This was the era of the starburst galaxy, where star birth was not confined to spiral arms but erupted across entire galactic bodies in ferocious, all-consuming bursts. The violence extended beyond individual galaxies. The cosmic web was denser, the universe was smaller, and galaxies lived in much closer quarters. This proximity made gravitational encounters far more frequent and dramatic. Galaxy collisions and mergers, which are rare, epochal events in today's universe, were commonplace daily occurrences. The sky of a planet in that era would have been a spectacular, ever-changing tapestry, with distorted galaxies and brilliant tidal tails frequently visible to the naked eye. And at the heart of this chaos, the supermassive black holes were feasting. With so much gas readily available from all the collisions and starbursts, these monsters were actively accreting material, blazing as quasars and active galactic nuclei with a ferocity seldom seen in the modern cosmos. The universe was louder, brighter, and far more violent. Cosmic noon was the universe's peak era of construction and chaos, a time when the foundational structures we see today were being forged in a relentless fire of creation. But like any fiery adolescence, it could not last forever. The brilliant firestorm of cosmic noon inevitably burned itself out, leaving behind a distinct population of galactic survivors. Among the most massive galaxies in the universe today, we find a somber and silent class, often called red and dead. These are the giant elliptical galaxies that dominate the centers of rich clusters, glowing with a uniform reddish hue. Their light tells a story of cessation. They are no longer forging new blue stars. Instead, their populations are entirely composed of ancient, cool, red stars that have been burning steadily for billions of years, with no fresh generations to replace them. They have run out of the cold gas required for star birth, and their story is one of galactic quenching, a process where the very mechanisms that create stars also work to permanently shut down the factory. One of the most effective quenchers is the supermassive black hole at the galaxy's heart, through a process called active galactic nucleus feedback. When a black hole feeds, the incredible energy it releases does not just create a brilliant quasar, it also drives powerful winds and heats the surrounding gas to extreme temperatures. This heated gas becomes too energetic to collapse and form stars. In some cases, the feedback is so violent it can blow the galaxy's entire gas reservoir out into intergalactic space. The galaxy, in a final, furious act of consumption, destroys its own future fuel supply. But there is another, more environmental cause. When a galaxy lives in a dense cluster, it faces a brutal commute. As it moves at high speed through the cluster's core, it plunges through the superheated intracluster medium, that thin, multimillion-degree gas that fills the space between galaxies. This is like holding a snowball in front of a blowtorch. The pressure of this hot gas rams against the galaxy's own cooler gas, violently stripping it away in a process called ram pressure stripping. What gas isn't ripped away is heated so intensely by the friction that it, too, cannot cool down and condense into stars. The galaxy is essentially sterilized by its own environment, its star-forming gas either stolen or rendered useless. Left with no fuel, the galaxy's stellar population simply ages in unison. The massive blue stars die off first, leaving behind the longer-lived redder stars. Over eons, the galaxy's overall color shifts from blue to yellow to a final, steady red. These red and dead giants are the cosmic equivalent of a retired industrial powerhouse, its furnaces cold, its workers aged, silently orbiting the cluster center as fading monuments to a more energetic and violent past. Yet even as violent mergers quench giant galaxies, they can also spark new creation in their outer debris. Tidal forces during a colossal collision do not merely tear material apart, they can also sculpt it into something entirely new and independent. When two large galaxies swing past each other in a gravitational dance, they pull immense plumes of gas and stars from one another, stretching them into long, graceful arcs known as tidal tails. These tails are not just temporary decorations, they can become stellar nurseries in their own right. Within these ejected streams, pockets of dense gas can cool, collapse, and ignite with star formation. If a knot within a tidal tail contains enough mass and its own gravity can overcome the expanding motion of the tail, it can pinch off and become a self-contained orbiting entity. This is the birth of a tidal dwarf galaxy. These are unique cosmic objects, unlike all other galaxies which form within and are dominated by massive halos of dark matter. Tidal dwarfs are born from the visible, ordinary matter stripped from galactic disks. They are composed almost entirely of the gas and stars that were once part of a larger galaxy's spiral arms. Consequently, they should contain very little, if any, dark matter, since the dark matter halos of the parent galaxies remain largely undisturbed and separate during the collision. This makes them fascinating natural laboratories. Observing them allows astronomers to study how stars and gas behave in the absence of that dominant, invisible scaffold. We have seen compelling candidates for tidal dwarfs in several famous galactic collisions, like the Tadpole Galaxy and the Mice Galaxies, where bright blue knots of newborn stars dot the ends of their spectacular tidal tails. These are not doomed orphans, they are survivors, potentially capable of lasting for billions of years as distinct, if small, galactic entities. So in the grand narrative of cosmic violence, a major merger is not purely an act of destruction. It is also a moment of unexpected fertility, scattering seeds of new galactic life from the wreckage of the old. But not all galactic offspring from collisions are so bright and fertile. Some of the universe's most mysterious residents are the spectral opposites of starbursts, vast, ghostly islands that seem to defy the very logic of star formation. They are called ultra-diffuse galaxies, and they are cosmic enigmas of scale and emptiness. Picture a galaxy the physical size of our Milky Way, spanning 100,000 light-years from end to end. Now imagine that instead of containing 100 billion stars, this enormous volume holds only about 1% of that number, perhaps a single billion suns scattered so thinly that the galaxy is almost transparent. That is an ultra-diffuse galaxy. They are not small, they are enormous, yet they are so faint that their starlight is barely a whisper against the blackness of space, which is why they remained hidden for so long, only coming to light with the most sensitive modern telescopes. Their existence poses a profound puzzle. They possess the same vast dimensions as a major spiral, suggesting they formed within a similarly massive dark matter halo, one with plenty of gravitational pull to gather an immense cloud of primordial gas. So what happened? Why did so little of that gas ever condense into stars? One leading theory points to a galactic infancy cut short. Perhaps these galaxies began forming stars early on, but then something robbed them of their potential. A nearby quasar's fierce radiation in the ancient universe could have heated their gas, preventing it from cooling. Or a close encounter with a larger neighbor might have tidally stripped away much of their star-forming material while leaving their dark matter halo and the sparse, already formed stars intact. Another, more intriguing idea is internal. Maybe the dark matter halo itself was too smooth, lacking the dense substructure that normally seeds pockets of gas collapse. Without these internal triggers, the gas simply never got dense enough to ignite widespread star formation, remaining a vast, quiet reservoir. These ghostly giants are a reminder that having the raw materials and the space to build is not enough. A galaxy also needs the right sequence of cosmic events to spark its stellar fires, and some, for reasons we are still deciphering, never received that crucial spark. Amidst the chaos of collisions, some encounters produce results of stunning, almost artificial symmetry. Floating in the void like a cosmic bull's-eye is Hoag's object, a galaxy so perfectly ringed it seems impossible. At its heart lies a dense, golden-yellow core of ancient stars, almost like a small elliptical galaxy. Surrounding this core is a vast, empty gap, a dark moat of near-nothingness. And beyond that gap shines a brilliant, perfect circle of young, blue stars and glowing pink nebulae, a ring of furious creation suspended in space. This is not a trick of perspective. It is a real, stable structure, and it represents one of the rarest galactic forms in the universe. How does nature craft such a precise shape from the messy business of gravitational encounters? The leading explanation is as violent as it is elegant. Imagine a quiet, orderly spiral galaxy, its stars orbiting peacefully in a disk. Now imagine a smaller, dense galaxy, perhaps a compact elliptical, plunging directly through the center of that disk, perpendicular to its plane, like a bullet fired through the center of a dartboard. This is not a glancing blow or a prolonged merger, it is a precise, head-on collision. The intruder does not linger, it passes straight through and continues on its way, largely unscathed. But its gravitational wake is catastrophic for the target. As the small galaxy punches through the dense central region, its gravity sends a powerful shockwave rippling outward through the disk. This wave compresses the galaxy's gas in a perfect, expanding circle, much like the circular ripple that expands when a stone is dropped into a still pond. This compression wave is a density wave, a moving zone of higher pressure. As it propagates outward from the impact point, it sweeps up the galaxy's interstellar gas, squeezing it violently. Where the wave passes, the gas reaches a critical density and ignites into a frenzy of new star formation. The result is a propagating ring of brilliant blue stars and stellar nurseries born in the wake of the cosmic bullet. The central bulge of the original galaxy, largely undisturbed by the passing intruder, remains as the bullseye. Over time, the ring expands and the initial burst of star formation within it fades, leaving behind the ghostly, perfect circle we see in objects like Hoag's object. It is a temporary, breathtaking monument to a single, perfectly aimed moment of cosmic violence, a splash frozen in time. Perfect cosmic rings are sculpted by precise violence, but another invisible force weaves through every galaxy, shaping its inner workings in profound ways. Beyond the gravity of dark matter and the light of stars, galaxies are permeated by vast, fragile webs of magnetism. These galactic magnetic fields are astonishingly subtle. The strength of the Milky Way's field is about 100,000 times weaker than the magnet holding a note to your refrigerator. Yet, despite this frailty, they are everywhere, stretching for tens of thousands of light years. They are not simple bar magnets with a clear north and south pole, but complex, tangled fields that follow the spiral arms, looping and twisting through the interstellar medium. You cannot see them directly, but their presence is revealed by their effect on light. As electrons spiral along these magnetic field lines at nearly the speed of light, they emit a faint glow in radio waves, a synchrotron radiation that traces the field's structure like cosmic iron filings. More dramatically, they align the dust grains that drift between the stars, causing them to emit polarized light, a subtle clue astronomers can measure to map the field's orientation across the sky. This invisible architecture does more than just create a faint radio whisper. It acts as a cosmic guidance system and a containment field. Charged particles, like the protons and atomic nuclei that make up cosmic rays, cannot travel in straight lines through a magnetized galaxy. They are forced to spiral along the magnetic field lines, zigzagging their way across interstellar space. This turns the galaxy's magnetic web into a labyrinth, trapping these high-energy particles for millions of years and dictating where they can go. This has a direct impact on the story of star formation. When a cloud of gas begins to collapse to form a star, it must shed its magnetic field. The field fights the collapse, providing a form of pressure that supports the cloud against gravity. For a star to be born, the gas must slowly leak across the field lines, a process called ambipolar diffusion, which acts as a cosmic brake, slowing down the entire process. Without magnetic fields, star formation might be a sudden, catastrophic collapse. With them, it becomes a more gradual, controlled event, potentially regulating the birth rate of stars across the galaxy. So these faint, pervasive fields are the silent conductors of the galactic orchestra, guiding cosmic rays, pacing stellar birth, and adding one more layer of invisible complexity to the island universes we call home. These faint magnetic fields will guide the final, fateful dance of our own galaxy. The Milky Way is not an eternal, isolated island. It is on a slow-motion, inevitable collision course with its largest neighbor, the Andromeda Galaxy. Right now, Andromeda is a faint, fuzzy patch in our night sky, but it is hurtling toward us at an astonishing 250,000 miles per hour. This is not a possibility, it is a certainty confirmed by precise Hubble Space Telescope measurements of Andromeda's sideways motion. The countdown stands at about 4.5 billion years. When the Sun has swelled into a red giant and the inner solar system is a scorched wasteland, the two great spirals will begin their gravitational embrace. The merger will not be a sudden crash. Galaxies are mostly empty space, so the stars themselves will rarely collide. Instead, it will be a stately, billion-year-long gravitational tango. As the galaxies first swing past each other, their mutual gravity will stretch them like taffy, pulling out magnificent tidal tails of stars that will arc across the heavens. The orderly disks will be shredded, their structures forever destroyed. Over multiple close passes, they will finally coalesce, their stars mingling into a new, chaotic swarm. The likely product is a giant elliptical galaxy, a smooth, football-shaped collection of ancient stars. Astronomers have already given this future entity a name, Milky. During the merger's peak, the night sky from any surviving planet would be a spectacle beyond imagination. Instead of a band of Milky Way, two colossal galactic disks would fill the sky, tilted at strange angles, their spiral arms visibly distorted. New bursts of star formation, ignited by the compressed gas, would light up like countless fireworks across the celestial dome. The familiar constellations would be utterly erased, their stars scattered into new patterns by the galactic turmoil. It is a future of both breathtaking beauty and absolute transformation, the final chapter in the life story of our galactic home, written by the same relentless gravity that built it from smaller pieces so long ago. The violent feedback from a black hole is not the only way to end a galaxy's star-forming life. There exists a slower, quieter, yet equally final fate, a cosmic form of starvation known as strangulation. This process targets the galaxy's lifeline, its supply of fresh, cold gas. Think of a galaxy not as a closed system, but as a living entity that needs to breathe. It constantly draws in pristine hydrogen from the vast filaments of the cosmic web, a steady inflow of fuel to replenish what is burned in its stellar furnaces. Strangulation occurs when that external supply is abruptly cut off. One of the most common scenarios happens when a spiral galaxy, like our own, falls into the dense, crowded environment of a massive galaxy cluster. As it makes this fateful journey from the lonely cosmic countryside into the crowded metropolitan core, it crosses a threshold. The superheated plasma that fills the space between galaxies in the cluster, the intracluster medium, acts like a scalding wind. This hot gas is so energetic that it prevents any new cold gas from the cosmic web from penetrating the galaxy's halo and reaching its disk. The galaxy's fresh fuel line is severed. Yet, inside the galaxy, life goes on for a while. The existing reservoir of cold gas within its spiral arms remains untouched at first. Stars continue to form at their normal pace, burning through this internal supply. But with no way to replenish it, the galaxy is living on its savings. Gradually, over hundreds of millions of years, the gas is converted into stars and locked away in stellar remnants. The blue light of young stars begins to fade as the galaxy's star formation rate steadily declines. The spiral arms, once traced by brilliant blue star clusters, grow dimmer and more diffuse. The galaxy's overall color shifts from blue to yellow and finally to a uniform red as the last of its gas is exhausted and only the long-lived cooler stars remain. This is a death by slow suffocation, a gradual fading of the lights rather than a dramatic explosion. Unlike the violent quenching from a central black hole, which can shut down star formation in a relatively short, tumultuous burst, strangulation is a lingering twilight. It explains the existence of many red and dead galaxies that show no signs of a violent merger or intense past feedback, their quiet demise written in the steady aging of their stellar population. They are galaxies that entered a hostile environment and simply, slowly ran out of breath. Our own galactic future is a slow-motion collision, but the deepest telescopes let us witness the universe's fiery birth. The current record holder for the most distant galaxy ever observed is a speck of light designated GNZ 11. We see this galaxy not as it is today, but as it was a staggering 13.4 billion years ago, when the cosmos was a mere 400 million years old. To grasp that scale, if the universe's entire history were compressed into a single calendar year, with the Big Bang at the stroke of midnight on January 1st, we are observing GNZ 11 in the pre-dawn darkness of January 10th. This is not just a distance record, it is the ultimate time machine. Because light travels at a finite speed, looking across cosmic distances is literally looking back in time. The photons that finally struck the Hubble Space Telescope's sensors had been racing through the expanding void for over 97% of the universe's existence, carrying a snapshot of an era just after the cosmic dark ages ended. What does this ancient fossil reveal? GNZ 11 is surprisingly small, only about 1/25th the size of our Milky Way, but it is forming stars at a ferocious rate, 20 times faster than our galaxy does today. Its very existence at such an early epoch challenges our models. It means that some galaxies assembled their first stars and grew to substantial mass with breathtaking speed, in a cosmic environment we are only beginning to understand. Observing these most distant galaxies is our only direct window into the universe's first chapters, allowing us to study the raw materials, the growth spurts, and the infant properties of the very first galactic building blocks. Each faint red-shifted smudge is a message from the dawn of time, telling us how quickly the cosmic darkness was pierced by the first islands of light. That ancient light from the dawn of time shows us the first structures, but a mystery closer to home forced us to rewrite the laws of the cosmos itself. For centuries, we believed a galaxy was simply what we could see, a collection of stars, gas, and dust bound together by their mutual gravity. This simple picture made a clear prediction about how a spiral galaxy should spin. Think of our solar system. The sun's gravity holds the planets in orbit, but its grip weakens with distance. Mercury, the innermost planet, whips around at a blistering pace. Neptune, far out in the cold darkness, moves in a slow, stately crawl. The same logic should apply to a galaxy. The visible mass, all the stars and glowing gas in the central bulge and disk, should act like the sun. Stars orbiting near the crowded center should zip around quickly, pulled by the strong gravity of all that luminous matter. But as you move out toward the galaxy's sparse outer edges, where stars are few and far between, the orbital speed should drop off dramatically, just like Neptune's slow orbit. This was the expectation, a clean and intuitive rule. When astronomers in the 1970s finally managed to measure the rotation speeds of stars and gas clouds across spiral galaxies, they were met with a result so shocking it overturned our fundamental understanding of matter. The data revealed a flat rotation curve. Stars and gas clouds orbiting far out in the galactic suburbs were moving just as fast as those near the bright downtown core. It was as if every planet in our solar system, from Mercury to Pluto, orbited the Sun at the exact same breakneck speed. This was impossible under the rules of gravity as we knew them. The only way to explain it was if there was far more mass in the galaxy than we could see. This invisible mass had to be distributed in a vast spherical halo that extended far beyond the galaxy's visible edge, enveloping the entire luminous disk. Its gravitational pull was keeping those outer stars moving so fast. This was the first direct, incontrovertible evidence for dark matter. The beautiful spiral we see is just the glittering tip of a colossal, invisible iceberg, its true shape and size dictated by a substance we cannot touch or see, a ghostly presence that holds the galaxy together from the shadows. That ghostly dark matter halo does more than just hold the galaxy together. It also serves as the ceiling for a vast, slow-motion rainstorm. Supernovae are not merely destructive in points, they are powerful galactic recycling engines. When a massive star reaches the end of its life and explodes, it does more than scatter heavy elements. The colossal blast sends a shockwave rippling through the surrounding interstellar medium, heating vast volumes of gas to millions of degrees and propelling it outward at tremendous speeds. This superheated material can achieve such velocity that it punches right through the thinner parts of the galactic disk, erupting into the cooler, more diffuse halo above and below. Picture a colossal fountain, not of water, but of incandescent plasma, shooting geysers of star-forged material hundreds or even thousands of light years into the galactic heights. These are galactic fountains in action. The ejected gas, now far from the dense disk, begins to lose its ferocious energy. It radiates heat away, slowly cooling over millions of years. As it cools, it condenses back into denser clouds, massive complexes of hydrogen and helium now laced with the iron, oxygen, carbon, and silicon forged in the stellar furnace that created them. Gravity then takes over once more. These now heavy, metal-rich clouds begin to fall back toward the disk, pulled by the galaxy's collective mass. They streak downward as gigantic, cold rain droplets on a cosmic scale, splashing back into the interstellar sea from which they came. This cycle is the galaxy's circulatory system. It constantly churns the interstellar medium, stirring the pot and distributing the products of stellar alchemy far from their birthplace. A supernova in one spiral arm can, over eons, seed clouds in a completely different arm with the heavy elements necessary to form rocky planets and, ultimately, life. Furthermore, this returning rain provides a continuous supply of fresh, cool gas, the essential fuel for the next generation of stars. Without this fountain and fallback, the galaxy's star-forming disk would quickly exhaust its local resources or become polluted with hot gas that cannot collapse. Instead, the violent death of stars ensures the continued fertility of the galaxy, a cycle of creation, destruction, and rebirth that turns stellar ashes into the building blocks of new worlds. The fate of a galaxy is not written solely by its internal fires, but by the neighborhood it calls home. Galaxies are cosmic social creatures, and their environment acts as a powerful, often brutal, sculptor of their destiny. This leads to a fundamental divide in galactic life stories, a contrast between the frantic, dangerous existence within a dense cluster and the serene, isolated journey of a field galaxy. Imagine a bustling metropolis versus a quiet farmhouse on a vast plain. The difference is that stark. A galaxy born or captured within a rich cluster, like the famous Virgo or Coma clusters, lives in a state of perpetual gravitational stress. Here, thousands of galaxies are packed into a relatively small volume of space, all orbiting a common center at incredible speeds. The sheer density creates a hazardous environment. Close encounters and even direct collisions are frequent, tearing apart spiral structures and triggering violent starbursts. But perhaps the most insidious threat is the intracluster medium, that superheated plasma fog between the galaxies. As a spiral galaxy plunges through this scorching gas at millions of miles per hour, it faces a relentless headwind known as ram pressure. This wind acts like a cosmic sandblaster, violently stripping away the galaxy's own cool, star-forming gas. The galaxy is effectively robbed of its future fuel, its star formation quenched in a process of environmental strangulation. Over time, such a cluster galaxy is likely to be transformed from a vibrant, gas-rich spiral into a smooth, red, and dead elliptical, its creative potential extinguished by the crowd. In stark contrast, a field galaxy lives in cosmic solitude. These are the islands that float in the great voids and less dense filaments of the cosmic web, far from the crowded cluster cores. Our own Milky Way is actually a field galaxy, the dominant member of only a small, loose collection called the local group. For a field galaxy, life is generally quieter and more self-determined. It is not constantly jostled by neighbors or scoured by hot intergalactic winds. It can hold onto its gas reservoirs for much longer, allowing for a more gradual, sustained pace of star formation. Its spiral structure, once formed, can persist for billions of years without being violently disrupted by a major merger. This does not mean its life is uneventful. It will still consume smaller satellite galaxies and may eventually merge with a large neighbor, as the Milky Way will with Andromeda, but the pace and pressure are vastly reduced. Its evolution is driven more by its internal clock and the slow consumption of its own gas, rather than by the relentless external forces of a hostile environment. The quiet field is where grand design spirals can maintain their majestic shapes across cosmic epochs. So, when you look at a galaxy's form, whether it is a disheveled, gas-poor elliptical or a pristine, star-forming spiral, you are not just seeing its mass or age. You are reading a biography of its social life, a record of whether it grew up in a crowded, violent city or on a lonely, peaceful frontier. The environment is the unseen hand that guides the galaxy down one of two very different paths toward its ultimate fate. Our own quiet, rural existence in the cosmic web has a name: the local group. This is our immediate galactic neighborhood, a modest, gravitationally bound family of about 60 galaxies drifting through a relatively empty patch of the universe. The local group is not a sprawling metropolis like the Virgo cluster. It is more akin to a small, isolated village in a vast countryside, with two grand manors and a scattering of tiny cottages. The two manners are, of course, our Milky Way and the magnificent Andromeda galaxy, each a spiral giant containing hundreds of billions of stars. They are the gravitational anchors of the entire group, around which all the smaller members orbit. The rest of the family consists almost entirely of dwarf galaxies, faint, diffuse collections of stars that are mere satellites to the two giants. Some, like the Large and Small Magellanic Clouds, are irregular, gas-rich companions visible to the naked eye from the southern hemisphere. Most, however, are elusive dwarf spheroidals, faint smudges of ancient stars so dim they were only discovered in recent decades, clinging to the halos of the Milky Way and Andromeda like cosmic moss. The entire group spans about 10 million light-years from one diffuse edge to the other, and it is held together by its own mutual gravity, a self-contained island in the expanding sea of space. This isolation is key because we are so far from the crushing density of a massive cluster. The galaxies within the local group have largely evolved at their own pace, free from the environmental stripping and constant collisions that shape cluster life. Our Milky Way's beautiful spiral structure has persisted for billions of years precisely because we live in this quiet suburb. The local group is our cosmic context, the small pond in which our galactic story has played out, a typical example of how most galaxies in the universe actually live, not in crowded clusters, but in small, quiet gatherings like our own. Within the bustling metropolis of a galaxy cluster, the true story is written in the faintest of glows. Beyond the brilliant disks and glowing cores of the individual galaxies, a ghostly light permeates the darkness between them. This is the intracluster light, a diffuse, ethereal glow from countless stars that no longer belong to any single galaxy. They are the lost citizens of the cluster, stars that have been violently evicted from their homes. The process is relentless. As galaxies swing past each other at tremendous speeds within the dense cluster, their immense gravitational tides pull and stretch them. These tidal forces are so powerful they can rip stars right out of the outer regions of galaxies, flinging them into the intergalactic void. The stars themselves are not destroyed, they are simply set adrift, condemned to orbit the cluster's center in the vast, empty spaces between the galaxies. Over billions of years, this gravitational harassment creates a pervasive sea of orphan stars, their combined faint light forming a soft, uniform backdrop to the sharper galactic pinpoints. This ghostly glow is incredibly difficult to detect, requiring exquisitely sensitive telescopes and careful processing to separate from the sky's natural brightness, but it is there, a permanent record of the cluster's violent past. And the sheer amount of it is staggering. In some massive clusters, this intracluster light can account for a substantial portion, up to 20% or more, of the cluster's total starlight. That means 1 out of every 5 stars in the entire cluster is a lonely wanderer, drifting in the immense dark between galactic cities. By mapping the distribution and color of this faint light, astronomers can literally trace the history of gravitational interactions within the cluster, seeing which galaxies have suffered the most stripping and when the most dramatic encounters likely occurred. It is a pale, silent census of cosmic displacement, proving that the violence of the cluster environment leaves a permanent, luminous scar. These orphan stars are the casualties of cosmic encounters, but sometimes a galactic collision can produce a structure of breathtaking geometry. Among the most visually arresting sights in the cosmos are polar ring galaxies, celestial marvels that look like a luminous hoop spinning around a galactic hub. Picture a standard spiral or elliptical galaxy as the central body. Now imagine a brilliant, thin ring of stars, gas, and dust orbiting not within the galaxy's plane, but perpendicular to it, circling the poles like a cosmic hula hoop. This ring is not a trick of perspective. It is a real, distinct structure orbiting at a right angle to the main disk. The most famous example, NGC 4650A, looks like a glowing jeweled band has been threaded through the center of a fuzzy elliptical galaxy. The existence of such a precise yet fragile configuration tells a dramatic story of galactic theft. The prevailing theory is that these rings are the captured remains of a smaller companion galaxy. Billions of years ago, a gas-rich dwarf galaxy ventured too close to a larger, more massive neighbor. Instead of being completely devoured in a chaotic merger, it was tidally shredded in a very specific way. As the dwarf was torn apart, its stars and gas were stretched into a long stream. If this stream was captured on an orbit that swung over the larger galaxy's poles, the material could gradually settle into a stable, rotating ring. Over time, the ring's own gravity and rotation would smooth it into the coherent, thin structure we observe. In other cases, the ring might form from gas directly stripped from a passing galaxy, funneled into this polar orbit. This configuration is more than just a beautiful accident, it is a powerful scientific tool. Because the ring orbits at a 90-degree angle to the main galaxy, it gives astronomers a unique three-dimensional view of the system. We can study the gravitational pull of the central galaxy by watching how stars and gas move within the ring, allowing us to map the shape and extent of the invisible dark matter halo in a way that is impossible with a flat, single-plane galaxy. The ring itself, often rich in gas and young blue stars, acts as a timestamp. Its chemistry and stellar population can be compared to the older stars in the central galaxy, revealing the age of the catastrophic encounter that created it. These celestial hoops are thus frozen moments of ancient violence. Their perfect perpendicular orbits a lasting signature of a long-ago act of cosmic capture, offering us a rare and stunning window into the dynamic history of galactic interactions. This cosmic transformation from blue to red is not a theory, it is a direct observation written across billions of years of light. In the late 1970s, astronomers Beatrice Tinsley, Harvey Butcher, and Augustus Oemler made a startling discovery by comparing nearby galaxy clusters to those incredibly far away. They found a profound difference in color. The distant clusters, whose light had traveled for billions of years to reach us, were filled with a higher proportion of blue, star-forming spiral galaxies. Their light was young and vibrant, but the nearby clusters, the ones we see as they are in the modern universe, were dominated by the red, serene glow of elliptical galaxies, their star-forming days long over. This shift, now called the Butcher-Oemler effect, is one of the clearest pieces of evidence we have that galaxies do not simply form and then remain static. They actively evolve, and their environment is the primary driver of that evolution. The dense, crowded core of a galaxy cluster is a galactic graveyard in the making. When a blue, gas-rich spiral falls into this environment, it faces a hostile takeover. The scorching intracluster medium strips its gas through ram pressure. Its close encounters with neighbors disrupt its delicate spiral structure, and the collective gravitational harassment from the cluster's dark matter halo pulls it apart. Over billions of years, these processes work together to quench its star formation, rob it of its identity, and transform it into a smooth, red elliptical. The Butcher-Oemler effect is the statistical proof of this life cycle. It shows us a time lapse of cosmic history, revealing that the serene, red giants dominating today's clusters were once the vibrant, blue spirals of a younger, more chaotic universe. The cluster itself is a giant engine of galactic evolution, and the changing color of its population is the exhaust from that engine, a permanent record of transformation written in starlight. That shift from blue to red is not an instantaneous flip of a cosmic switch. Galaxies spend billions of years in a transitional state, a kind of cosmic adolescence where their fate hangs in the balance. Astronomers see this phase clearly when they plot galaxies on a simple chart, a color magnitude diagram. On one side, you have the red sequence, a tight band of old, quiescent elliptical galaxies glowing with the steady light of ancient suns. On the other side lies the blue cloud, a scattered population of vibrant spirals, their light dominated by the fierce blue glow of young, massive stars. Between these two distinct realms lies a sparsely populated gap, a kind of no-man's land astronomers call the Green Valley. Galaxies found here are neither fully blue nor fully red. They possess a greenish tint in their overall light, a subtle blend of the blue from their dwindling star formation and the red from their aging stellar population. This Green Valley is not a permanent home, it is a corridor. A galaxy passing through it is in the critical act of quenching, of shutting down its star-forming engines. It might be a spiral that has used up most of its internal gas, slowly fading as its last blue stars die off. Or it could be a galaxy recently subjected to environmental strangulation in a cluster, its fresh gas supply cut off, now living on its dwindling savings. These Green Valley galaxies are precious snapshots of a galaxy in midlife crisis. By studying them, we can catch the precise mechanisms of quenching in action. Are powerful winds from a central black hole blowing the gas away? Is the gas simply being heated so it cannot collapse? The Green Valley offers a living laboratory to watch a galaxy transform from a vibrant, star-forming entity into a quiet, red and dead retirement home. Finding oneself in the Green Valley means the galaxy's most creative and energetic days are behind it, and a long, serene fade into the red sequence awaits. The serene red giants and vibrant blue spirals tell only part of the cosmic story. Some of the most revealing characters in the galactic drama are also the smallest and faintest. Dwarf galaxies like the Draco or sculptor dwarf spheroidals orbiting our Milky Way are cosmic underdogs. They contain only a few million stars, a mere flicker compared to our galaxy's hundreds of billions. Yet these tiny, diffuse smudges of light hold a profound and counterintuitive secret. They are not mostly made of the stars we see. They are, in fact, the most dark matter-dominated objects in the entire universe. Within a dwarf galaxy, the visible stars are just a tiny, glittering tracer, a handful of luminous breadcrumbs adrift in a massive, invisible sea of dark matter. The ratio is staggering. In a large spiral like the Milky Way, dark matter outweighs normal matter by about 5 to 1 in the extended halo. But in a dwarf spheroidal, that ratio can explode to hundreds or even thousands to 1. Imagine a vast, empty sports stadium. Now place a single, lit match in the very center. The light from that match represents all the stars in the dwarf galaxy. The immense, dark volume of the entire stadium represents the unseen dark matter halo that envelops them. The stars are not what holds the galaxy together. They are merely prisoners of an immense, ghostly gravitational well. This makes these faint galaxies exceptional natural laboratories. Because they have so few stars and almost no gas, the complicating effects of stellar winds and supernova are minimal. Their dynamics are governed almost purely by gravity, and that gravity is overwhelmingly supplied by dark matter. By meticulously tracking the motions of just a few dozen individual stars within a dwarf, astronomers can map the shape and density of its dark matter halo with exquisite precision. These quiet, ancient stellar fossils are therefore our clearest windows into the nature of the universe's most abundant yet most mysterious substance, proving that the darkest places often hold the brightest clues. The central bulge of a spiral galaxy is not always the same kind of structure. In fact, astronomers now recognize two distinct types, each telling a completely different story about the galaxy's past. The first is the classical bulge. This is what many of us picture, a large, round, and dense swarm of stars at the galaxy's heart, resembling a miniature elliptical galaxy embedded within the spiral disk. The stars in a classical bulge move on chaotic, random orbits, buzzing around the center like a furious swarm of bees. This chaotic motion is a key clue to its violent origin. Classical bulges are thought to be built primarily through the colossal mergers we discussed earlier, when smaller galaxies crashed into the young Milky Way. Each major collision would violently scatter stars into the center, puffing up this central region into a round, disordered ball. The classical bulge in our own galaxy is a fossil of that ancient, tumultuous era, a relic of the hierarchical assembly that built our cosmic home from smaller pieces. The second type is far more orderly, and it goes by the name pseudobulge. Unlike the round classical bulge, a pseudobulge is flatter, often shaped more like a football or even a central bar of stars. Crucially, the stars within it don't swarm chaotically. Instead, they orbit in an orderly, rotating disk, much like the stars in the galaxy's outer spiral arms, just in a more compact region. This orderly rotation points to a completely different origin story, one not of sudden violence, but of slow, internal evolution. Pseudobulges are thought to form through a process called secular evolution, a gentle reshaping driven by the galaxy's own internal dynamics over billions of years. As the galaxy's spiral density waves or central bar rotate, they can slowly funnel gas and stars inward toward the center. This inward migration causes material to pile up, building a bright, dense central concentration that is still fundamentally part of the disk, not a separate, merged entity. A beautiful example of a galaxy with a prominent pseudobulge is M94, also known as the Cat's Eye Galaxy. Its center shines with an intense, compact light, but that light comes from a flattened disk of stars, a testament to a quieter, more self-made history. The existence of these two bulge types reveals a fundamental fork in the evolutionary road. One path is shaped by external violence, the other by internal, patient rearrangement. Looking at a galaxy's heart, we can now read whether its central character was forged in the fires of ancient collisions or sculpted by the slow, steady hand of its own rotating disk. Our own star is on an epic voyage through its galactic home. The Sun is not a stationary beacon at the center of things. It is a traveler, orbiting the heart of the Milky Way at a breathtaking 230 kilometers every single second. This grand circuit, one complete revolution around the galactic center, takes approximately 230 million years to complete. Astronomers call this span of time a cosmic year. The last time our solar system was in this same position relative to the galaxy, the dinosaurs were just beginning their long reign on Earth, but this journey is far more complex than a simple, graceful circle. If you could trace the Sun's path through the galaxy, you would see it follows a slightly stretched elliptical orbit. We are not always the same distance from the bustling galactic center. At our closest approach, we are pulled a bit inward, and at our farthest, we drift a bit outward, riding the gentle wave of the galaxy's gravitational field. Even more intriguing is our vertical motion. The Milky Way's disk is not a perfectly flat plane. It has a subtle thickness and warp. The Sun does not glide precisely along the midline. It bobbles up and down, oscillating through the disk like a cork floating on a slow cosmic ocean. We are currently north of the galactic midplane, moving upward, and will continue to do so for millions of years before gravity pulls us back down again. What drives this complex, weaving path? The galaxy is not a smooth, featureless gravitational bowl. Its structure tugs at us from all sides. The dense spiral arms we admire from within exert their own gravitational pull, subtly herding stars as they pass. More significantly, the Milky Way's central bar, that long, dense structure of stars at its heart, is a powerful dynamical engine. As the bar rotates, its immense gravity creates resonances, rhythmic tugs that can nudge stars into these elliptical and oscillating orbits. So our solar system's journey is a dynamic dance, a response to the symphony of mass that makes up our galaxy. We are not just orbiting a point, we are navigating a living, rotating structure, our path a permanent record of the Milky Way's invisible forces. This means our cosmic neighborhood is always changing, and over hundreds of millions of years, the view from Earth shifts entirely, offering new vistas of the galaxy's brilliant core and its sparse outer halo. This journey through the crowded core of a galaxy cluster is a perilous one. The space between galaxies there is not empty, it is filled with a thin, superheated gas known as the intracluster medium. For a spiral galaxy rich with cold hydrogen, this environment is a cosmic wind tunnel. As the galaxy plows through this tenuous but scorching plasma at millions of miles per hour, it experiences a brutal force called ram pressure stripping. Picture a tree in a hurricane. The powerful wind does not tear the tree from its roots, but it violently strips away every leaf and small branch. Ram pressure works in a similar, devastating way. The galaxy's stars and dark matter halo are held fast by gravity, like the tree's trunk and roots, but its interstellar gas, the cold, diffuse clouds that float between the stars, has a much weaker grip. The headwind from the intracluster medium slams into this gas with immense force. It does not gently push it, it grabs it and rips it directly out of the galaxy's gravitational embrace. You can actually see this happening in stunning telescopic images of galaxies like those in the Virgo cluster. Long, faint streamers of hydrogen gas, glowing in radio waves, trail behind the galaxy like the tattered remains of a cosmic banner, marking the path of its stolen atmosphere. The consequence is immediate and severe. That cold gas is the raw fuel for new stars. Once it is stripped away, the galaxy's star-forming factories are starved. The brilliant blue knots of young stars in its spiral arms begin to fade, and no new ones ignite to replace them. The galaxy's color shifts from blue to yellow, then red. Its elegant spiral structure, deprived of the glowing stellar nurseries that define it, becomes blurred and indistinct. Often, what remains is a lenticular galaxy, a ghostly disk without arms, or it may be transformed entirely into a smooth, red elliptical. This is not a slow process of internal aging. It is a rapid environmental assassination. A galaxy can lose its entire gaseous reservoir in just a few 100 million years, a blink in cosmic time. Its vibrant life is cut short not by a grand explosion, but by the relentless, invisible wind of the space it dared to traverse. This invisible architecture, from the smallest dwarf to the largest cluster, finds its ultimate origin in the faintest glow imaginable. Stretching across the entire sky is the cosmic microwave background, a cold, uniform bath of radiation left over from the Big Bang itself. But this afterglow is not perfectly smooth. Embedded within it are the faintest of temperature variations, tiny patches where the ancient plasma was a fraction of a degree warmer or cooler. These are not random imperfections. They are the direct, frozen imprints of those quantum density seeds, stretched to cosmic proportions by inflation. Think of the universe at 380,000 years old, a searing fog of plasma finally cooling enough for atoms to form and light to travel freely. The photons released at that moment have been racing toward us ever since, carrying with them a snapshot of that infant cosmos. The slightly denser regions where dark matter had already begun to pool appear as slightly cooler spots in the microwave background. Why cooler? In those denser patches, photons had to climb out of a slightly deeper gravitational well, losing a tiny bit of energy which we perceive as a lower temperature. The map of these hot and cold spots is therefore a baby picture of the universe's gravitational potential, a blueprint of its future structure. When cosmologists run supercomputer simulations of cosmic evolution, they don't start with a blank slate. They start by inputting the exact pattern of fluctuations observed in the cosmic microwave background. They then let the laws of physics, dominated by dark matter and dark energy, play forward over 13.8 billion years. The result is astonishing. The simulated universe that emerges from those initial conditions looks, on the largest scales, exactly like the one we observe. The simulations produce a cosmic web of filaments and voids, with galaxy clusters forming at the intersections, matching the statistical distribution of galaxies in our sky with remarkable precision. This is one of the greatest triumphs of modern cosmology, the whisper from the dawn of time imprinted on the cold microwave sky, successfully predicts the grand, glittering architecture of galaxies we see today, connecting the first instant to the present in a single, unbroken chain of cause and effect. Those supercomputer simulations are more than just predictions. They are entire virtual universes born from equations and running on silicon. The most advanced projects with names like Illustris TNG and EAGLE are not simple animations. They are colossal computational experiments that begin with a nearly uniform, expanding box of virtual space, seeded with the same tiny density fluctuations we see in the cosmic microwave background. Then the programmers set the rules, the known laws of physics, and hit start. Gravity acts on both dark matter and normal matter. Gas follows the laws of hydrodynamics, flowing, heating, and cooling. Stars form according to our best models, and when they die, they explode as supernova, injecting energy and heavy elements back into the system. Even the growth and feedback from supermassive black holes are included. The simulation then runs forward across billions of years of cosmic time, all compressed into months of supercomputer calculation. The result is not a single galaxy, but a vast, evolving cube of virtual cosmos, containing tens of thousands of galaxies that form, merge, and evolve on their own. The true test is in the comparison. When astronomers analyze this synthetic universe, they find an uncanny match to reality. The virtual galaxies span the same range of sizes, shapes, and colors as those we observe through our telescopes. They fall along the same red sequence and blue cloud in color magnitude diagrams. They exhibit the same relationships between a galaxy's mass and its star formation rate. They even show the same large-scale structure, a cosmic web of filaments and voids where galaxies cluster in the simulated data just as they do in our sky. These virtual universes are our ultimate testing grounds. When a theory about, say, how black hole feedback works is programmed in, we can watch the consequences play out across an entire cosmos and see if the resulting galaxies look right. If they don't, the theory needs revision. It is a profound cycle where observation inspires the simulation, and the simulation, in turn, refines our understanding of the very laws that built everything we see. Einstein's theory of general relativity gave us more than an explanation for gravity. It gave us a tool to see the invisible. His equations predicted that massive objects warp the fabric of space-time, and that light, traveling through this warped geometry, would follow a curved path. This means a colossal concentration of mass, like a galaxy cluster, can act as a gravitational lens, bending the light from objects directly behind it. The effect transforms the cluster into a natural cosmic telescope, one far more powerful than anything we could ever build. When the alignment is perfect, the light from a single, extremely distant galaxy can be bent around the foreground cluster, smeared and stretched into multiple distorted images. Sometimes these images form graceful arcs of light, like celestial smiles curving around the cluster's core. Other times they appear as multiple mirrored copies of the same galaxy, arranged in a perfect Einstein ring. This is not an illusion, it is nature's ultimate magnifying glass. The magnification factor can be enormous, amplifying the light of a background galaxy by 10, 50, even 100 times. Suddenly, a galaxy so far away it is normally just an indistinct red smudge becomes a resolved object. Astronomers can study its internal structure, map its star-forming regions, and even discern individual, brilliant clusters of stars within it, details completely lost without this cosmic assist. Gravitational lensing lets us peer deeper into the universe's past than ever before, revealing the infant forms of galaxies in the early cosmos with a clarity that would otherwise be impossible. It is a direct validation of relativity written across the sky, and a reminder that sometimes to see the most distant lights, we must first learn to see the bending of space itself. Gravity's grand design holds even stranger patterns than we first imagined. On the largest scales, galaxies do not simply float in random orientations like leaves on a pond. They show a mysterious tendency to align with the invisible architecture of the cosmos itself. One of the most puzzling observations involves the giant elliptical galaxies that sit at the hearts of massive clusters. Their shapes are not randomly tilted. Studies have found that the long axes of these central galaxies often point toward the neighboring clusters and filaments of the cosmic web, as if they are aware of the larger structure around them. It is as though the galaxy knows which way the cosmic roads run, aligning itself with the highways of dark matter that fed its growth. This alignment suggests that the entire cluster and the galaxy at its core did not form in isolation. They were spun up and shaped by the gentle, cosmic-scale tidal forces exerted by the surrounding web as it pulled matter into the cluster's gravitational well over billions of years. The galaxy's final orientation is a fossilized record of that directional inflow, a permanent pointer to the source of its own construction material. This cosmic coordination extends to smaller scales in a way that has become a genuine headache for theorists. Look at our own Milky Way. Its satellite dwarf galaxies, like the large and small Magellanic Clouds, are not scattered in a messy, spherical swarm around us as the simplest dark matter models would predict. Instead, they orbit in a startlingly thin plane, a vast disk-like arrangement that seems far too organized to be random. This is not unique to our galaxy. The same phenomenon appears around our neighbor, Andromeda, whose satellites also seem to prefer orbiting in a narrow plane. These structures are called satellite planes, and they are incredibly fragile. In the dynamic, chaotic environment of a galactic halo, such thin, coherent disks of satellites should be easily disrupted and scattered by gravitational interactions over cosmic time. Their continued existence suggests they are either much younger than we think, or they formed together in a way our current models struggle to explain. Some scientists propose they are the fossil remnants of ancient tidal tails, born from a single, colossal collision between galaxies long ago. Others wonder if they point to flaws in our understanding of how dark matter flows and clumps on small scales. These aligned satellites are like a chorus singing in perfect harmony when we expected a cacophony, a beautiful but confounding pattern written in the motions of the faintest galactic lights. These aligned satellites present a beautiful but baffling pattern, yet they point to an even deeper cosmic puzzle, one that lurks in the emptiness around us. Our most sophisticated simulations of cosmic evolution, based on the cold dark matter model, paint a very specific picture of a galaxy like the Milky Way. They show that our vast dark matter halo should be swarming with thousands of smaller satellite halos, the gravitational seeds for dwarf galaxies. These are the predicted building blocks left over from our galaxy's hierarchical assembly. Yet, when we look up, we find a profound mismatch. We observe only a few dozen dwarf galaxies orbiting the Milky Way, not thousands. This glaring discrepancy is known as the missing satellites problem. Where are all the predicted galaxies? Astronomers have proposed two compelling and perhaps complementary solutions. The first is that the dark matter halos are indeed out there by the thousands, but they are utterly dark. They contain no stars, no gas, not a single spark of light to betray their presence. How could this happen? In the earliest universe, the ultraviolet radiation from the first generation of stars and galaxies was intense. This cosmic background radiation could have heated the gas within the smallest, lowest mass halos, preventing it from cooling, condensing, and collapsing to form stars. These halos would have been stillborn, gravitationally intact but forever dark, invisible islands of pure dark matter adrift in our galactic halo. The second possibility is that our understanding of galaxy formation on the smallest scales is incomplete. Perhaps supernovae in these tiny protogalaxies were so powerful that they blew out all of their gas, permanently halting star formation after only a brief initial burst. Or maybe the complex interplay between dark matter and ordinary matter, particularly in these low-mass environments, is more subtle than our simulations can currently capture. The truth likely involves both ideas. Some halos may indeed be dark, while others that did manage to form a few stars might be so incredibly faint and diffuse that they blend into the background glow of the night sky, escaping our detection. This cosmic census is far from complete. Every time a new, ultra-faint dwarf galaxy is discovered on the outskirts of the Milky Way, it chips away at the problem, but the fundamental gap between prediction and observation remains one of the most significant clues that our map of the cosmos, especially on the smallest scales, is still missing critical details. The universe's teenage years were not just a time of chaos but of astonishing efficiency. Deep within the cosmic noon, astronomers have spotted a peculiar class of objects, galaxies so compact and ferocious they earn the name blue nuggets. These are not the sprawling, majestic spirals of today. They are cosmic powerhouses, tiny in size but impossibly dense, often no larger than a few thousand light-years across, which is minuscule compared to our 100,000 light-year-wide Milky Way. Yet within that tiny volume, they pack a stellar mass rivaling our entire galaxy, and they are burning through their gas at a rate that defies belief, forging new stars hundreds of times faster than we do now. From a distance, they appear as brilliant blue pinpricks, their color a direct result of the intense, short-lived, massive blue stars being born in a continuous, violent firestorm. This furious activity cannot last. The blue nugget phase is a galaxy's ultimate growth spurt, a brief but spectacular burst of construction that likely lasts only a few 100 million years. The driving force behind this incredible compaction and star formation is thought to be a perfect storm of conditions in the early universe. Vast rivers of cold gas were flowing along the filaments of the cosmic web, funneling into the centers of growing dark matter halos with incredible efficiency. This rapid, focused inflow of fuel created an environment of extreme pressure and density, igniting star formation at a pace that is almost unimaginable in the cosmos of today. But such ferocity carries the seeds of its own destruction. The very stars being born so rapidly will die young in supernova, and the central supermassive black hole, also feasting on the abundant gas, will eventually awaken. The combined energy from these processes likely unleashes a galactic wind of catastrophic power, blowing away or heating the remaining gas in a final, quenching feedback event. With its fuel supply severed, the star formation shuts down almost completely. The brilliant blue stars quickly burn out, leaving behind the longer-lived redder stars. Over billions of years, the galaxy's color transforms from that intense blue to a golden yellow, and finally to the red hue we associate with old stellar populations. Without new gas to rebuild a disk, and having been born compact and dense from the start, these blue nuggets are the leading candidates for the infant forms of today's giant elliptical galaxies. They are the universe's overachievers, building an entire galaxy's worth of stars in a tiny, furious flash, before settling into a long, quiet retirement as the red and dead giants we see at the heart of modern clusters. The galactic core is a place of unimaginable density and violence. If you could stand on a hypothetical planet near the Milky Way center, the night sky would be a blinding, perpetual daylight, lit by millions of stars packed together 1,000,000 times more tightly than in our quiet solar neighborhood. Here, stars are not light years apart, but mere light days or even light hours from one another, engaged in a frantic gravitational dance. This stellar metropolis is home to some of the galaxy's most bizarre phenomena. Streaking through this region are immense, mysterious filaments, long strands of magnetized material that glow in radio waves, each one stretching for dozens of light years. They look like cosmic harp strings vibrating in the magnetic fields that permeate the core, though their exact origin remains one of the Milky Way's great puzzles. And presiding over this entire frenetic district is the supermassive black hole itself, Sagittarius, a star. While currently quiet, its gravitational influence is absolute. We see stars whipping around this invisible point at speeds exceeding 15 million miles per hour, their elongated orbits tracing out the shape of a terrifying gravitational well. Occasionally, it stirs. Clouds of gas that venture too close are stretched and heated, flaring brightly in X-rays before their material vanishes across the event horizon. Studying our own relatively tame central monster is a priceless opportunity. It acts as a nearby, slow-motion laboratory for understanding the furious quasars and active galactic nuclei in distant galaxies. By watching how Sagittarius, a star, interacts with the gas and stars in its immediate vicinity, we can decipher the physics of accretion and feedback on a human, or rather, a galactic scale. Our front row seat to this chaotic core reveals the gentle giant our black hole can be, but also the sleeping power it holds, a direct link to the universe's most luminous and destructive engines. The life of a galaxy is not a straight line but a complex, self-regulating loop. This grand cycle, a feedback loop of staggering scale, connects every process we have explored into a single, interdependent story. It begins with the simplest act, the cooling of pristine hydrogen gas within the dark matter scaffolding. As this gas cools, it condenses into dense clouds and gravity takes over, collapsing these clouds to ignite the first stars. This is the ignition of the galactic engine, but the story does not end with creation, it pivots to destruction. The most massive of these new stars live fast and die young. Their deaths in supernova are not merely endpoints, they are transformative events. These explosions blast newly forged heavy elements into space and, more crucially, drive powerful shockwaves through the surrounding gas. These shockwaves can compress other clouds, triggering more star birth, but they also create vast, hot bubbles that push outward, driving galactic winds. Simultaneously, some of the infalling gas feeds the supermassive black hole at the galaxy's heart. When this monster feasts, it unleashes a different kind of fury. The energy from its accretion disk and its relativistic jets pours into the galaxy, heating the surrounding gas to extreme temperatures or blasting it entirely out into intergalactic space. Here lies the critical balance, the feedback. All this energy from stars and black hole, whether it is a gentle heating or a violent expulsion, works against the initial condition. It counteracts the cooling. The very processes that require cool gas to begin with end up heating that gas or removing it entirely. This creates a self-regulating thermostat. If star formation runs too hot and too fast, the resulting supernova and black hole activity will quickly heat or eject the remaining fuel, putting a brake on the frenzy. If things are too quiet, the gas can cool unimpeded, eventually reaching the densities needed to ignite a new wave of star formation, which will then awaken the feedback mechanisms once more. This delicate dance between creation and destruction, between cooling and heating, dictates a galaxy's personality. A grand design spiral maintains its graceful arms because this feedback is in a relatively stable equilibrium, with star formation and gas recycling in a steady rhythm. A red and dead elliptical, however, represents a loop that has been permanently broken. Its feedback events, likely during a ferocious merger or starburst, were so violent they ejected the gas reservoir forever, shutting down the cycle and leaving the galaxy in a permanent state of quiescence. We are here on a rocky planet orbiting a stable star because our galaxy has managed this feedback loop with a remarkable, though not perfect, balance for billions of years. This delicate feedback loop that defines galactic life will one day run its final cycle, peer forward across an almost incomprehensible span of time to an era trillions of years from now. The universe we would recognize will have vanished, transformed by the relentless work of dark energy. Remember, dark energy is not a force that pulls or pushes matter directly. It is a property of space itself that causes the very fabric of the cosmos to expand at an ever-increasing rate. Today, that acceleration is subtle, only noticeable across the vast voids between superclusters. But given enough time, its effects become absolute. In this distant future, the expansion of space will have accelerated to such a degree that the cosmic web itself will be torn apart. The great filaments that once channeled gas into galaxy clusters will stretch thin and finally snap. Each galaxy cluster, each gravitationally bound family like our local group, will become an isolated island drifting in an ever-widening sea of perfect blackness. From the perspective of any one cluster, all other structures will have been pushed beyond the cosmic horizon. Their light, no matter how powerful, will no longer be able to reach across the expanding gulf. The universe will appear empty, a void containing only the stars of one's own immediate galactic family, surrounded by an impenetrable curtain of darkness. Within these isolated islands, the story turns inward and grows dim. The era of star formation will have long since ended. All the usable gas will have been either converted into stars, locked away in stellar remnants like white dwarfs and neutron stars, or blown out into intergalactic space by those final, powerful feedback events. No new stars will ignite. The existing stars, however, will continue their slow burn. The massive, brilliant blue stars died off first in mere millions of years. The sun-like stars, like our own, will exhaust their fuel over billions of years, swelling into red giants and then fading into white dwarf embers. The last stars to shine will be the faint, miserly red dwarfs, the smallest and most frugal of stellar engines. These tiny stars can fuse hydrogen for trillions of years, but even they are not eternal. One by one, over an epoch so long it makes the current age of the universe seem like a single blink, the last red dwarfs will finally sputter out. What remains will be a cosmos of ghosts. Galaxies will no longer be recognizable as spirals or ellipticals. They will be diffuse, darkening clouds of stellar corpses, black holes, and cold, rocky planets all orbiting in silence. The supermassive black holes at their centers will have consumed the last scraps of matter within their reach and will also fade into quiescence. The universe will enter a final, cold, and dark equilibrium, a state of maximum entropy where no energy gradients remain to drive any process, where no new light is ever created. This is the ultimate fate implied by our current understanding, a quiet and lonely end to the brilliant, violent, and creative epic of galactic evolution. The majestic whirlpools of stars we see today are not permanent. They are brilliant but temporary blooms in a cosmic spring that will one day give way to an endless, silent winter. Every atom in your body heavier than hydrogen or helium tells a story of cosmic violence. The iron in your blood, the calcium in your bones, the oxygen you breathe, none of these elements existed in the universe's first moments. They were forged in the furnaces of stars and scattered across the galaxy by titanic explosions, a legacy written into our very chemistry. Consider carbon, the fundamental backbone of all known life. It was not created in the Big Bang. It was born in the hearts of stars like our Sun, through the slow, steady fusion of helium nuclei over billions of years. For more massive elements, the story is far more dramatic. Iron, the element that gives our blood its red color and our planet its solid core, represents a stellar endpoint. It is the final element a star can create through normal fusion, as making anything heavier actually consumes energy. To forge the elements beyond iron, the nickel, zinc, copper, and gold requires a cataclysm. These are created in the final seconds of a massive star's life, during the unimaginable pressure and neutron flux of a supernova explosion, or in the even more extreme collisions of neutron stars. Once forged, these newly minted atoms are not kept secret. The supernova blast hurls them outward at a significant fraction of the speed of light, injecting them into the surrounding interstellar medium. Over millions of years, these enriched clouds of gas, now seeded with the ingredients for planets and life, mix with the broader galactic reservoir. They become part of the great cycle of galactic fountains and rain, eventually cooling and condensing into new generations of stars and planetary systems. Our solar system formed from such a cloud about 4.5 billion years ago, a cloud that had been enriched by the deaths of countless stars that lived and died before our sun was even a glimmer. This means the carbon in your cells was once part of a red giant star. The oxygen you just inhaled was fused in a star more massive than our sun. The gold in a wedding ring was likely forged in the collision of two dead stellar cores, a neutron-star merger that occurred billions of years ago in a distant spiral arm. We are not just observers of the galactic story, we are its literal product. Our bodies are temporary collections of atoms that have journeyed across light years and through stellar interiors, assembled by the gravitational mechanics of our galaxy into a form that can, for a fleeting moment, contemplate its own ancient and stellar origins. You are not simply in the universe in a very direct and physical sense is in you. The story of the galaxies, from quantum seed to cold ember, is a chronicle we are still learning to read. Our current chapter is one of anticipation, standing on the brink of a new era of cosmic vision. The next generation of telescopes, both in space and on remote mountaintops, are not merely upgrades. They are time machines and dark matter mappers of unprecedented power, ready to fill in the blank pages of our galactic history book. Leading this charge is the James Webb Space Telescope. Unlike Hubble, which sees primarily in visible and ultraviolet light, Webb is an infrared observatory. This is its superpower. The most distant galaxies in the universe have their light stretched or red shifted into the infrared part of the spectrum by the expansion of space. Webb is designed to capture that stretched light, to see the first galaxies not as they are today, but as they were when they were truly forming during the era of cosmic dawn and cosmic noon. It is already peering into nurseries of infant stars hidden behind veils of dust, studying the atmospheres of exoplanets for the chemical signatures of life, and resolving the faint structures of those ancient protogalaxies in stunning detail, telling us exactly how chaotic and furious those first building blocks really were. On the ground, a different kind of revolution is brewing. The Vera C. Rubin Observatory, with its gigantic 3.2 billion pixel camera, will conduct a 10-year survey of the entire southern sky, not once but over and over. This relentless scanning will create the deepest, widest movie of the universe ever made. It will detect billions of new galaxies, far too faint for current telescopes to see, and it will watch for changes, catching fleeting events like supernova and the subtle warping of light from gravitational lensing on a colossal scale. This immense statistical map will allow us to trace the distribution of dark matter with a precision never before possible, testing our models of the cosmic web's evolution against a dataset of almost unimaginable size. And looking ahead, the European Extremely Large Telescope, with a primary mirror nearly half the size of a football field, will use its phenomenal light-gathering power to do something astonishing: directly image Earth-like planets around other stars and study the chemical composition of individual stars in galaxies far beyond our local group. It will watch stars orbiting the supermassive black hole at the center of a distant galaxy, not just our own, and analyze the gas in galaxies so far away we see them as they were just a billion years after the Big Bang. Together, these new eyes on the cosmos promise to transform our understanding. They will find galaxies that challenge our theories, map the invisible scaffolding of dark matter in 3 dimensions, and perhaps even catch the very first generation of stars as they flicker on, illuminating the end of the cosmic dark ages. The next chapter of the galactic story is not yet written, but the tools to write it are now opening their lenses to the sky. 50 facts have taken us across 13.8 billion years of cosmic history, yet the story of galaxy formation is far from a closed book. For every mystery we have solved, a deeper, more fundamental question has emerged from the shadows. We stand at a frontier, our map of the cosmos still filled with blank spaces labeled "Here be dragons." The greatest of these unknowns is dark matter itself. We have mapped its gravitational influence with exquisite detail. We know it weaves the cosmic web and cradles every galaxy, but we still do not know what it is. Is it a sea of exotic, undiscovered particles, trillions of which pass through your body every second without a trace? Or does it point to a flaw in our understanding of gravity itself, a need to rewrite Einstein's rules on the largest scales? Until we solve this, the true foundation of every galactic structure remains a ghost. Then there is the breathtaking speed of the early universe. How did supermassive black holes weighing billions of suns manage to form in less than 1 billion years? That is a cosmic heartbeat. Did they grow from impossibly massive first stars, or did they collapse directly from enormous clouds of primordial gas, leaping into existence as ready-made monsters? Their frantic early growth defies our smoothest timelines, and within the galaxies themselves, the precise mechanics of life and death remain elusive. What is the exact sequence that triggers a galaxy-wide starburst, and what is the specific combination of stellar winds and black hole fury that finally flips the switch to quench it forever? We see the before and after, but the moment of transition is still hidden. These are not failures of understanding, they are the signposts of a vibrant living science. Each unanswered question is an invitation, a new chapter waiting to be written by the next observation, the next simulation, the next generation of thinkers looking up at the stars. The universe has given us 50 answers, and in return, it has offered us 50,000 new mysteries to pursue. From those first quantum whispers to the final, fading embers of red dwarf stars, we have traced the universe's most magnificent epic. We have seen how invisible dark matter weaves the cosmic web, how titanic mergers forge elliptical giants from spiral chaos, and how the supermassive black hole at a galaxy's heart can dictate its very destiny. Every spiral arm is a cosmic traffic jam, every red and dead galaxy a monument to ancient violence, and every atom in our bodies a relic of stellar furnaces that died billions of years ago. Our own Milky Way is a cannibal, a spinner of stars, and a traveler on a 230 million-year orbit, all while on a slow-motion collision course with Andromeda. This story transforms the night sky from a static tapestry into a living, breathing chronicle. When you look up, you are not just seeing points of light. You are seeing gravitational seeds stretched to a cosmic scale. You are witnessing the faded glow of galactic feasts, and you are observing the temporary, brilliant bloom of stellar creation in a universe that is mostly dark, silent, and unknown. We are the universe contemplating itself, built from its stars and shaped by its history. So the next time you stand under a clear, dark sky, remember the epic written in that darkness. Which fact from this cosmic journey resonated most deeply with you? Was it the ghostly influence of dark matter, the inevitable future collision of our galaxy, or the stellar origin of the atoms in your hand? Share your favorite cosmic revelation in the comments below. If you want to keep exploring these mysteries, subscribe and join us as we continue to unravel the secrets of the cosmos, one astonishing discovery at a time. The universe's story is vast, and our chapter in it is just beginning. Keep looking up.